In this video, we'll look at real numbers and the number line. Please write down all the definitions and take notes in your math notebook, and please complete all practice problems there as well. So let's first look at simplifying square root expressions. When I see this first problem here, the square root of 25, I'm asking myself what number times itself is equal to 25? Well, the answer there is 5. 5 times 5 is equal to 25. Next, I have the square root of 9/16. I want to ask myself what number times itself will be 9/16. Well, I know 3 times 3 gives me 9, and 4 times 4 gives me 16. So the square root of 9/16 is 3/4. So let's see that again. So let's say if I say the answer is 3/4, then I should be able to take 3/4 times 3/4 and get 9/16. Well, 3 times 3, that's equal to 9, and 4 times 4 gives me my 16. And finally, I want to know what's the negative square root of 64. So here I'm asking myself what negative number times itself is equal to 64. Well, I know 8 times 8 gives me 64, so the negative square root of 64 is negative 8. Okay, because negative 8 times negative 8 will give me a positive 64. So when I am simplifying these square root expressions, I have certain numbers here that we saw earlier. They're called perfect squares. And these are numbers whose square root is an integer. That's the definition of a perfect square. So for instance, 4 would be a perfect square because I get an integer as my answer for the square root of 4. The square root of 4 is 2. 15 is not a perfect square because there is no integer when I multiply it by itself that will give me 15. I know 4 times 4 will give me 16, I'm close, but there's no integer that will give me 15. And finally, 1 is also a perfect square because the square root of 1 is just 1. 1 times 1 gives me 1. We can estimate square roots. In this case, I want you to round it to the nearest whole number. So if I'm looking for the square root of 52, and I want to estimate what that might be, well, I think about the perfect squares that I know. So I know 49 is a perfect square because 7 times 7 is 49. I know 64 is a perfect square because 8 times 8 gives me 64. So if I am looking for an estimate of the square root of 52, well, I'm going to say that's going to be closer to 7 because 52 is much closer to 49 than it is to 64. So that's my estimate of the square root of 52. Alright, some vocabulary to get down. So we'll start with natural numbers, the first numbers you learned. These are all the counting numbers starting with 1. So for instance, we have 1, 2, 3, 4, and so on and so forth. Then we have whole numbers. And these are all of our counting numbers, the ones that we looked at previously, and 0. So 0 is included in a whole number. Our whole numbers are 0, 1, 2, 3, 4, and so on. Third, we have integers. These are all positive and negative numbers with no fractional parts, and 0 is also an integer. So negative 2, negative 1, 0, 1, 2, those are all integers. If I had something like negative 4 8/10, this is not an integer because it has that decimal piece to it. Next, we have rational numbers. Rational numbers can be written as a fraction with an integer in the numerator and the denominator. So, for instance, a number like negative 3 over 8. Negative 3 is an integer, 8 is an integer, so negative 3/8 is what we call a rational number, right? So then we know that's equal to negative 0 and 375 thousandths when I convert that to a decimal. So negative 0 and 375 thousandths would also be an integer, or the percent version of this, negative 37.5%, also an integer. Up next we have irrational numbers, and these are numbers that cannot be written as a fraction with two integers. The square root of 10 is an example of that, so let's take a look at the square root of 10. If I wanted to find the square root of 10, I get this long decimal, 3.16227766, and notice this decimal keeps on going. It actually doesn't stop here at the 7. It goes on forever, and there's no repeating pattern when you look at these decimals. So this square root cannot be written as a fraction with two integers, so this is an irrational number, right? So this is approximately equal to, 3 1600ths, but that is just an approximation of it. It's not what it actually is equal to. And last, all real numbers are made up of all rational and irrational numbers. So all the rational numbers, numbers that can be written as a fraction with an integer in the numerator and denominator, and all irrational numbers, these are all our real numbers. So now, thinking about those definitions, I want to name the subsets of real numbers to which each of these belongs. 77. Well, is 77 a whole number? Yep, 77 is a whole number. Is 77 an integer? Sure, 77 is an integer. Is it a rational number? Yes, I could write 77 as a fraction. 77 over 1 makes it rational. Is it irrational? Does it have a decimal that goes on forever with no repeating pattern? No, it doesn't, so it's not irrational. Let's look at our next example, the negative square root of 144. Well, I know the negative square root of 144 is going to be negative 12. Is that a whole number? Nope, because whole numbers are not negative. Is it an integer? Sure it is. Is it rational? Can I write it as a fraction? Sure I can. Negative 12 over 1. And finally, the square root of 14. Well, 14 is not a perfect square. If I try to find the square root of 14, I get this long decimal that goes on forever with no repeating pattern. And so this number here is irrational. Alright, now I just want to compare these real numbers here. So I've got the square root of 85 and 9 1/5. It's a little bit difficult to compare these because they're two different forms, but I can find the square root of 85, and that is approximately equal to 9.2195. And I know 9 1/5 is equal to 9 2/10. So 9.2195, which is the square root of 85, is going to be greater than 9 1/5. So I'd put the greater than sign there. Alright, here are some problems to practice on your own. Please complete each problem and then answer them in your books. Square root of 121, what number times itself is 121? That is simply 11. Number 2, the square root of 25 over 49. I think to myself, what's the square root of the numerator and what's the square root of the denominator? The square root of the numerator is 5. The square root of the denominator is 7. Next, I want to name the subsets of real numbers to which each of these belong. Is it a whole number? Is it integer? Rational? Irrational? Can be more than one? Negative 56 is not a whole number because it's negative, but it is an integer, and it can also be written as a fraction with an integer numerator and denominator, so it's rational. It is not an irrational number. The square root of 33. Well, that's 33 is not a perfect square, so this is an irrational number. And finally, 12/19. Well, it's not whole. It's not an integer because it's a fraction. It is rational. It has an integer in the numerator and the denominator. Alright, next I want to compare each of these using the less than or the greater than sign. Square root of 31 and 5 and 57 hundredths. So let's compare those two. I want to find the square root of 31, and that is 5.567 and so much more. And we can see that that is actually less than 5 and 57 hundredths. Alright, let's look at number 7, negative 21 eighths and the negative square root of 4. Well, let's start with the negative square root of 4. That is just going to be a negative 2. And negative 21 eighths. Well, I know that 8 will go into 21 twice, and I'll get 16. And then I will have 5 eighths left over. But this is negative. So now which is smaller, negative 2 and 5 eighths or negative 2? Negative 2 and 5 eighths is smaller, so I put the less than sign. And that's how we work with real numbers